Hello everyone, welcome to another video tutorial on SIFT. Today we will be using the application as a data cleaning or quality assurance tool. You will learn how to check for and correct faulty force assignments from all files loaded into the application at once. This feature of SIFT can save the user a significant amount of time as they will not have to go through each trial to evaluate the errors. This is particularly useful for lab managers or supervisors who may not be familiar with the raw data, but it can also be useful for collaborators that weren't involved in the collection process. As always, we will start with the data needed for the completion of this video tutorial. This tutorial uses an example dataset containing overground walking data from 4 subjects. The subjects walked at 3 different speeds: slow, normal, and fast. The data was analyzed using a pipeline which included an automatic gate event detection command. Link model-based items, including right and left ground reaction forces, were created using a pipeline as well. This data is reflective of a typical outcome from batch data analysis in Visual 3D. These data files can be downloaded using the link available on the HasMotion wiki page. As always, when we start a tutorial, we will need an empty project in SIFT. We must follow a uniform process each time we are loading in the workspaces. Click on the Load Library button in the left sidebar to open the Load Library dialog. Then we can click Browse and select the folder where the workspaces are stored. In this case, it is the 4 subjects walking data. So we can navigate to where this folder is stored and click on it and click on Select Folder. Now we can load in the dataset. This may take a while as the size of the dataset is larger than usual. Once loaded, we are able to see the workspace files in the main widget. Each workspace file has multiple C3D files with different walking speeds identified using tags. The plus button can be used to expand the subject file, revealing the trials and selected tags. Here we can see the fast, normal, slow, and then static tags. Now we can navigate to the Explore page to construct queries using the left toolbar. Throughout this tutorial, we will be wanting to explore ground reaction forces across the right and left gate cycles. We will be creating a query that contains 2 conditions, one for the right ground reaction forces and another for the left. How we define the conditions will determine how SIFT extracts the signals from the workspace's data tree. We can select the Query Builder icon to open the Query Builder dialog. To create a new query definition, we can click the Addition button in the Empty Queries list. For the name, we can type in GRF, or Ground Reaction Force, in the text box and click Save. As the query is still selected, it will prompt you to fill in a condition name where we will type in R_GRF, or Right Ground Reaction Force. Now we can explore the 3 tabs in order to define the subgroup. First is the Signals tab. This will allow the user to select specific signals according to their names in the data tree. For this tutorial, we can select the following. For the type, we can select link_model_based. For the folder, we can leave it on original. For the signal name, we can select R_GRF. And for the component, we select Z. Moving on to the Events tab, where it allows the user to specify the desired event sequence to extract the data from. For example, the right gate cycle could be extracted using the event sequences such as R on to R off, or RHS to RHS, standing for right heel strike. For this tutorial, we can select R on and R off as the event sequence, and leave the default normalization values of 101 for the number of points, and the spline type can be left as cubic. Now moving on to the Refinements tab, which allows the user to refine their selected signals using 2 separate and distinct methods. The first being according to tags and the other being according to the signals contained within the workspace files. For this tutorial, we can check off the Refine Using Tag selection and leave the others unchecked. We can select slow, normal, and fast tags and now click Save. This process must be repeated for the second condition within the same group to account for the left side. Now for the left side, we can right-click the subgroup we made, which is present in the conditions list, and click Reflect. This will automatically create a second condition for the other side, taking the signal from L_GRF. We can now overview the changes which this reflect feature has made. The Signals tab should remain uniform with the right side, and the only change that is made is the signal name to L_GRF as seen. In the Events tab, the event sequence is now L on and L off. The Refinements tab should also be uniform with the right side, where the Refine using tag selection is selected and the slow, normal, and fast tags are selected as well. Now in the left widget of the Query Builder dialog box, we can see one query, GRF, and in the queries list, there's two conditions, R_GRF and L_GRF. At this point in this tutorial, these definitions have been created, but signals have not been extracted from the loaded library. To do this, we have to click the Calculate All Queries button on the bottom of the dialog box. If you want to save this query definition, select Save Query Definitions on the top right of the dialog box. Now we can close the Query Builder dialog box and begin to examine the results by visually looking at the data through different plots. To create the plot for analysis of the example dataset, we must first make sure the plot type is set to signal time. Select the loaded group GRF and check Select All Workspaces. Now we can open the Data Styles option and make sure the Display Styles From is set to Workspaces, which it is. So now we can make sure that Plot All Traces is checked, and now we can refresh the plot, and as we can see, this is the plot we are given. We can use our cursor to select lines by left-clicking on them, where a tooltip appears giving us some information about that trace. We can unselect a trace by selecting Ctrl-H or selecting the Refresh Plot button. Now, as we can see in this example, there are some incorrect force assignments. In order to exclude these incorrect assignments, we can select any lines that may be a result of a bad event by left-clicking on it. If we want to exclude a single trace, we can right-click after, click Exclude, and exclude trace raw data. Now we can see that this trace has been excluded. For the obvious bad events, it is possible to click and drag over multiple traces on the plot to select them simultaneously. So, in this case, we see that this bottom part may be a result of a bad event. So, we can click and drag by left-clicking and dragging over the traces that we wish to exclude, and then right-clicking and then doing the same and clicking Exclude Trace. Now we can see that our data is much cleaner. We can verify that the desired traces have been properly excluded by checking the Workspaces section for the X replacing the original check mark beside each workspace. If we expand the workspace, we can see that a lightning bolt should replace the check mark beside each C3D file with some excluded traces, but not all. If you have accidentally excluded any data, you can right-click on the workspaces and select Re-include Data. If you want to visualize the data you have excluded alongside the remaining data, we can go to the General Options dialog on the upper taskbar and then select Show Excluded Data and the Use Specific Styles for Excluded Data option. Now we can unselect this and refresh the plot with all the workspaces, and as we can see, the excluded trials are included within our plot. It's except in red color, so we know which ones are. At times, we may want to examine a trace more closely before deciding to exclude it. We can select the traces of interest and right-click to open the pop-up menu to click Show Animation. So, for this trace, as we can see, the first one we've excluded, we can click on it, right-click on it, and then Show Animation. Now we can watch this animation to see exactly what is going wrong with this trace and why we wish to exclude it. Once you have made all of the desired exclusions, the original data is ready to be updated. Now that the incorrect force assignments have been identified in the dataset, it is possible to update the original CMZ data by clicking the Update CMZ Files item on the upper toolbar to open the dialog. The Excluded Traces option allows the user to add a bad event if they want to exclude the data traces. This option is helpful if the intention is to tag the bad data, reopen the original data, and make manual corrections one trace at a time. Alternatively, the Update Force Assignment option actually removes the force assignment from the original data. This option should be used if the user does not intend to revisit the original data after the modifications have been made. Just a note, this second option changes the underlying data. Reperforming this tutorial with newly saved data will produce different results. We can check off both in this case. Now we can select Add Event to exclude signals. And we can name the event r_bad just to differentiate it from the bad event that was already created. And we can also select update force assignments using excluded query data and have the option here with force and grf. Then we can select run pipelines. This results in Sift opening each CMZ file in the background, adding a bad event for the excluded traces, and removing the force assignments. This process can take some time depending on the CMZ size, but you can further explore your data as it occurs. When the update is complete, the checkmark icons will return beside each workspace in the Workspaces widget, and the original data will be modified. In this tutorial, you learned how to use Sift as a data cleaning tool for quality assurance purposes. Here the process of loading data, defining queries, excluding data, and updating the original data are described. Thank you for watching.